We count in tens, 10 digits, 10 tens to 100. We do it so naturally that we think of base 10 as absolute mathematical law. But the reality is much simpler. We count in tens because humans have 10 fingers. Math itself is flexible. It's just a system of grouping. Step into Nakasero Market and you'll see different rules apply. A farmer selling eggs or arranging produce doesn't always group by 10. They might bundle items by the dozen or in trays of 30. If we had 8 fingers instead of 10, our counting system would look like these market stalls, organized by a different bundle size. Modern machines operate on an even simpler rule. Computers group data using 2 states, on or off. This is base 2, or binary. To understand how digital technology processes information, we have to learn how to count using that specific bundle size. We can visualize this using an Ekikolo abacus, a banana stem with 3 sticks. Instead of ones, tens, and hundreds, these columns represent powers of 3. From right to left, we have the ones, the threes, and the nines. A number base only uses digits up to 1 less than the base itself. Base 3 only uses 0, 1, and 2. When we count, we drop 1 bottle top, then a second. They fit in the ones column. But when we add a third top, the column is full. The rules of base 3 require us to clear the ones and carry over 1 bundle into the threes column. Working in a new number base is not about learning new math. It is simply a matter of changing the limit for when a column fills up, forcing you to bundle items and move to the left. When writing a number in another base, the vocabulary changes. We do not read this as 124 because hundreds and tens are specific to base 10. We read it as written, 1, 2, 4, base 5. To find the base 10 value of this number, we map out the place values. Each position is a power of 5. From right to left, we have 5 to the power of 0, 5 to the power of 1, and 5 squared. Since any number to the power of 0 is 1, these columns represent 25s, 5s, and 1s. Now we expand the number. Multiply the digits by their column values. 1 group of 25, plus 2 groups of 5, plus 4 groups of 1. That gives us 25 plus 10 plus 4, resulting in 39 in base 10. The expansion method works for any base. You are taking the grouped items, the 25s and the 5s, and unbundling them until they are counted as individual ones again. Converting from base 10 into a new base uses the inverse operation. We use successive division to determine how many bundles of the new base size we can create from our total. To convert 27 into base 4, we divide 27 by 4. That gives us 6 with a remainder of 3. Next, we divide that 6 by 4, getting 1 with a remainder of 2. Finally, 1 divided by 4 gives us 0, with a remainder of 1. These remainders are the digits of our new number. To write the final answer, read the remainders from the bottom to the top. This gives us 1, 2, 3, base 4. Successive division is the mechanical process of sorting a large quantity into the specific bundle sizes required by the new base. We can add numbers in other bases using the same logic. In the problem 3, 4, base 5 plus 1, 2, base 5, we start with the right column. 4 plus 2 equals 6. Since base 5 only allows digits up to 4, we have to rethink how we record that 6. We take those 6 items and form 1 bundle of 5. We carry that bundle over to the next column and record the 1 item that remains behind. The mechanics of carrying are the same as standard addition, only the capacity of each column changes depending on the base. Consider a practical scenario. A librarian in Kampala uses a digital system that stores book codes in binary. One book has the code 11011. The next book on the shelf has a code it is 101 higher. When we add these in base 2, a column fills up at 2. So 1 plus 1 gives us a 0, carry the 1. That carry triggers a chain reaction through the next 3 columns, resulting in 100000 base 2. To summarize, every base has a digit limit. You expand using powers to reach base 10, and you divide to move away from it. When adding, you carry the moment a column reaches the base number. Number bases show us that our standard way of counting is a choice, not a requirement. By understanding how to group and carry in binary, You are using the same mathematical principles that allow digital circuits to process information and solve problems.